Okay, so let's begin the first session of the day. So it's my great pleasure to introduce Professor Edoardo Charbon, a pioneering figure in the field of quantum sensing and imaging and a longtime member of the ICCP community. After receiving his PhD from Berkeley in 1995, Edoardo spent time in industry, first at Cadence and then at Canesta. Before joining the faculty at EPFL, then Delft University, and finally returning to EPFL, where he has been leading the Advanced Quantum Architecture Laboratory for approximately 10 years now. Edoardo has been the driving force behind the development of deep submicron CMOS SPAD technology and has been instrumental in bringing about a single photon imaging revolution in computer vision, computational imaging, and 3D sensing. He has also pioneered the use of cryo-CMOS technology for the control of quantum devices, especially qubits, to achieve scalable, fault-tolerant quantum computing. Professor Charbon is a fellow of the IEEE, a distinguished visiting scholar of the W.M. Keck Institute for Space at Caltech, and has received the 2023 International Image Sensor Society's Pioneering Achievement Award. So please join me in welcoming Professor Edoardo Charbon.
Thank you very much, and I hope you can hear me without any issues. First, I'd like to start thanking the organizers that invited me here. It's a pleasure being at ICCP, a conference that I love for its vibrant research community and its burst of innovations. Unfortunately, I can't be with you today, but I hope you'll enjoy the talk nonetheless. So I'd like to start thanking the people of the ARPA Lab and its funders who make this research possible. Let me just start from imaging, quantum imaging. So quantum imaging is more or less defined as an imaging modality that enables certain type of detection capabilities and is based on the use of entangled photons and single photons. So these are some of the examples of various quantum imaging modalities that you will see, and we're going to talk about some of this today. What is typical of quantum imaging is that it requires either single photon granularity or picosecond time stamping, and sometimes both. And this is the reason why I decided to call this talk Picosecond Photography. So let me give you an example, starting from quantum distillation. In quantum distillation, and this is an example from the paper appeared a few years ago by Defiant and others, essentially you are looking at various information that can be hidden in plain sight. So in other words, you can have a classical image superimposed with a quantum image. And the quantum image is based on the use of entangled photons. So here, in this case, you have a generator of entangled photons, which can be mixed with conventional, with classical photons, for example, generated here. And here's an example of the dead cat and the alive cat that can be separated by using entangled photons. So, is this practical? Well, entangled photon generation is indeed practical. It's perhaps not the most efficient way of generating entangled photons, but it is doable. Quantum optics is a well understood field, and passive components are the usual ones. What about single photon detection? Single photon detection requires single photon detector as well as photon counting capability and single photon imaging. Are these possible? Well, in terms of single photon detection, we need a single photon resolution. In terms of single photon counting, we need a high timing resolution. And single photon imaging, we need a high spatial resolution and readout speed for real-time operation. Luckily, this has evolved in the last few years, yielding a technology known as SPAD, or single photon avalanche diode. These are not the only single photon detectors, but they're the ones that can be implemented in CMOS technology. So how does a SPAD work? A SPAD is essentially a diode reverse bias above breakdown. So if you reverse bias a diode above breakdown, you don't immediately have an avalanche, but you can actually operate in Geiger mode. So in Geiger mode, your optical gain is essentially infinite, but at the same time, it requires the detection of single photons. And this is due to the fact that for a very short amount of time, these curves actually continue straight, and it doesn't yield an avalanche until a later time. So if you have this capability, then you can implement this detector in CMOS technology. CMOS technology uses junctions, like in this case, a SPAD is made of a junction P plus and P well in deep retrograde N well. Now, with this implementation, it is indeed possible to build a detector that is not only CMOS compatible with a technology that is quite with a small feature size, but it can be especially very suitable for submicron processes, and is also compatible with triple well processes. Most importantly, it is reproducible, reliable, and miniaturizable. And we'll see later why that is so important. So these are some of the examples of SPADs that have been implemented in over the years. So this was perhaps the first fully depleted SPAD that allowed detection of with very high sensitivity, even at 900, 950, and even 1000 nanometer wavelength. More recently, SPADs have been implemented for UV and near UV SPADs with the peak sensitivity in the order of 90%. So this essentially could enable resolution sensitivity similar to conventional technology. And very recently, backside illumination has been introduced in SPADs. So in principle, the avalanche occurs at the top of the detector. The detector is reversed and is then bonded using hybrid bonding to another chip that does the electronics interpretation. So SPADs are very, very fast. So this is an example of 3 types of SPADs that have been implemented recently in relatively old technology, 180 nanometers. So here you see the diode, the quenching, and very fast recharge electronics. This way you can actually generate a pulse of about 1 nanosecond in size for each photon that is detected. This is essentially enabling you to achieve a very, very low dead time and very high levels of saturation. So this is a detail of the detector where you can see the round detector surrounded by the electronics. With this detector, we could achieve 100 CPS, or counts per second, dark count rate, down to a 0.2 CPS at minus 60 degrees, an optical sensitivity in the order of 55%, and also the capability of detecting electrons and converting electrons into pulses. So this is a very interesting capability because essentially it opens up the door to detection of X-rays and free electrons directly. Most importantly, this detector was able to achieve a timing resolution full width and half max in the order of 10 picosecond, and more recently the world record, which is a single photon time resolution of 7.5 picosecond, full width and half max. So this is not all that happened in the last few years. Timing resolution was improved dramatically, but also sensitivity was improved dramatically, as we have seen, up to 90%. The fill factor is relatively small so far, but it could be improved using micro lenses. That time can be reduced to the order of nanoseconds, dark counts in the order CPS or milli-CPS even, and after pulsing has been critically reduced. So microlenses can be built in large numbers. These are examples of square microlenses that essentially enable the fill factor to be increased up to 80%. So how do we achieve imaging? That is achieved with large format SPAD cameras. Large format SPAD cameras require first that the pixel be reduced. And this pixel has been reduced over the years. And recently at last ICCP in 2003 actually announced the world record in pixel pitch of 1.8 micrometer achieved with the help of 3D stacking. Of course, low pitch is not the only thing. You also need high performance and high fill factor, even though you're reducing the pitch. So in order to improve the fill factor, in order to improve sensitivity, recently people have come up with 3D stacking. 3D stacking is a way of taking the detector and hybrid bond it together with another chip and then reverse it and then thin it on the other side in order to be able to allow light to come from the other side and create and trigger the avalanches. 3D stacking can also be used in front-side illumination. For example, if you want to detect photons at the surface or if you have electrons that you want to detect directly. So these are examples of the technology that requires the true silicon vs to be implemented. So these are two examples. One built in TSMC technology that is now commercially available, and another one in using true silicon vs implemented in 180 CMOS image sensor technology. So this was the first chip that was built that achieved a megapixel in SPAD arrays with a pitch that is relatively high, 9.4 micrometers. At the time we used a technology that is relatively old, 180 nanometer, but nevertheless we were able to achieve the first megapixel camera. You can see immediately some of the interesting properties. One of them is the frame rate, which is 24,000 frames per second, and also a gating capability of 3.8 nanoseconds. With gating, one can achieve essentially an electrical or electronic shutter that is very, very short and very, very sharp. So these are details of the two type of pixels that we implemented. Now, thanks to the gating that is short but also highly controllable, one can, in principle, reconstruct the light as it propagates and it arrives to the detector. And so by building a histogram that essentially allows you to find the time of flight and the time of arrival of light. So this also allows you to implement fluorescence lifetime imaging microscopy, for example, or FLIM. And this is done by simply taking a gate and move the gate later in time. However, high overlapping is possible, and indeed the response of the film response can be reconstructed very nicely. So this is an example of a 3.64 megapixel image obtained in collaboration with Daniele Faccior's group, where we actually were able to perform film over a very large scene. Another thing that I mentioned earlier is the capability of detecting time of flight. In time of flight, essentially you're taking the photons that are emitted from a source, and with the help of a very advanced stopwatch, usually a TDC, one can reconstruct the distance from the source to the object and to the detector by this simple formula. Now, this is the theory, but in principle what happens is that when you're sending a pulse of light over the free space, you're going to have a lot of noise photons, some produced by some being dark photons, dark pulses, and some of them are photons produced by the background. And so that the question is how to distinguish those. And so this is essentially easy if the background noise is low, but if the background noise is high, like in this case, it can be even higher than the pulse that you're trying to detect, then it becomes a bit more difficult. So what we've introduced is a technique known as coincidence detection that allows you to distinguish photons that are essentially generated by the pulse from the background. And this allowed us outdoor with a background illumination in the order of kilolux to achieve distances in the order of hundreds of meters. So this way we are able to actually reconstruct the image at very, very large distance, even with the 50% reflective target. Now, coincidence is very useful for a number of other applications. For example, if you can build a G2 for light, you can use coincidence, for example, to determine spatial temporal coincidences that allows you to determine the type of light that you're emitting or the type of detection or absorption that you're observing. This is an example obtained from a paper published recently by colleagues. You can also perform anti-bunching detection. Anti-bunching occurs when two photons are reaching a beam splitter, and therefore they can take two different paths, and you can indeed obtain the knowledge about the fact that photons, the single photons have detected, have been reaching the beam splitter. So this is very useful in number physics imaging, and also can be very useful in this application where electrons are essentially converted directly into pulses, as I've shown earlier. Now, the critical parameter in time gating is the profile. So you need a profile that is highly reproducible and controllable, whose starting and end is highly controllable. This is an example obtained with MegaX, where we have a controllability in the order of a few picoseconds, and a full width of maximum 150 picosecond for the rise time and fall time. So this way you can build two-dimensional imaging and also three-dimensional imaging with the same detector. You can also perform the so-called light in flight. So this is an example of a pulse of light that gets propagated through C-space through various mirrors, and this was obtained again using multiple gates over a very short distance. So this is a 6.4 nanosecond event. This is an example of photons that can be detected in real time. This is an example of the last 100 frames detected of an array of 48 by 64 pixels. So I'd like to share some of the latest trends in chips for detection of single photons at very high timing resolution. The first one is Linux SPAD2, which is a reconfigurable SPAD array. So the idea here was to have a detector that is, each detector that is connected through an FPGA, and the FPGA was able to be reconfigured, for example, to be a counter or to be a time-to-digital converter. So this is an example of various pixels that achieve a timing resolution in the order of 15 picoseconds to 20 picoseconds. But the beauty of this approach is the fact that you can instantaneously convert the setup to be either a TDC or a set of counters or gated counters or other architectures. And this can be done through the fact that FPGA can be reconfigured. Another trend that I've seen recently is the use of detectors at very low temperature. So here we were able to measure the minimum dark count in the order of 10 millicps at 77 Kelvin, and then an increase again at the very low temperatures in the order of 4 Kelvin due to an increase of 1 RF noise that increases therefore after pulsing. But most importantly, what you can see here is that irrespectively of the temperature, the time resolution remains very, very good in the order of less than 100 picosecond full width and half max. So what about other wavelengths? So it is impossible to detect the photons in silicon higher than 1,000 nanometers unless quantum dots are used. So we used a combination of an in-gas indium gallium arsenide SPAD array. In this case, it's a small 96 by 96 array in combination with a silicon chip. And the silicon chip is essentially able to reorganize the pixels and also perform recharge and quenching. So this is a micrograph of the chip and the sensitivity from 950 to 1550 nanometers. Another trend is to increase automation. So this is an example where we used neural networks to interpret film in real time. With the help of neural networks, actually the interpretation of film can be done in a very short amount of time and thereby enabling even larger detection. In this case, it's only 32 by 32 pixels with a very, very high timing resolution and at the same time high accuracy. Embedded ANNs are actually been done in two new chips, one known as MindHive that you can see here on the left-hand side, another one known as Kelpie, which is going to be published later this year. There's also a very interesting development in industry. For example, Novovitz that is developing fast cameras capable of detecting single photons. And at the same time, cameras that can implement neural networks in situ. What about applications? So we talked about only LiDAR and film, but there are many, many more applications. So this is an example of ghost imaging that was implemented with SPADs. So you can see here two pico images, SPAD arrays of 32 by 32 pixels arrays with two different paths, the signal paths and the idler paths. And this is a reconstruction with a correlation function, again using correlation of entangled photons and essentially using various interpretation of the data, whereas here you can see that without the knowledge of entangled photons it's not possible to reconstruct the image. Another collaboration with Milena D'Angelo, University of Bari, we are performing correlation planoptic imaging. So in this case, we use a double path on the same detector or double detectors, performing essentially the same interpretation for the refocusing, like in any planoptic camera, and the super resolution processing. This is another example of an ultra-fast planoptic camera for particle tracking. In this case, neutrinos going through scintillators can essentially be tracked by use of a main lens and the SPAD array with the micro lenses. So this is a classical planoptic camera that is essentially capable of retracing the paths using in 3D using various fast algorithms. So the microlens center is used to determine the angle of running photons, and intersection points of multiple photons is used to reconstruct particle tracks. So this is the result of a collaboration with Davide Scalaberna at ETH Zurich. So what can we do recently in LiDAR? Actually, we've demonstrated recently a again, same detection capability at 100 meters and with a very large background illumination, 100 kilolux. But instead of this being done on a few pixels, this was done simultaneously on 320 by 240 pixels. So this is an example of the return paths. The reconstruction is done the usual way, and this is the reconstruction obtained at 1.7 meters, 26 meters, and up to 100 meters. So here you can see that, for example, the image is completely oblivious of the large background illumination that you see here. But what is very interesting here is the fact that the overall power dissipation per pixel was reduced to 3.88 microwatts, which is, I think, one of the smallest ever demonstrated. We have also demonstrated LiDAR with fluorescence detection at the same time. This is work done in collaboration with Petr Brusa at Dartmouth College. And so here you can see again, using gating, one can simultaneously reconstruct the film and the position of the emitting molecules. Recently, in collaboration with Andreas Felten at the University of Wisconsin at Madison, we were able to achieve a non-line of sight imaging. And non-line of sight imaging in this case, unlike LiDAR, is in this case we use the floor for emitting, for the first emission of the light coming from the laser, and then reconstruction using Andreas' algorithms by using another technique known as gradient gating. In gradient gating, essentially we're simultaneously testing various pixels for and gating the light, the return light, from very large reflections coming, for example, from the first bounce, and therefore being able to distinguish the first bounce from the third or even the fifth bounce. So this is an example of a measurement achieved with a chip known as Chameleon that will be presented in SCIRC this year in a couple of months. So you can see the photomicrograph of the chip. So in this way we were able to achieve reconstruction in 3D of the letters, and also, of course, conventional LiDAR. I'd like to conclude the applications with Quanta burst photography. This is an application that was introduced by Mohit Gupta at the University of Wisconsin. And essentially the idea here is to reduce the size of the emission of the size of the frame from relatively long exposure to much shorter exposures and single photon detection capability. So in this case, notice that no read noise is observed. And also, of course, with capability of a much faster detection, also comes the fact that you need to compensate for potential movements. So this is work published in 2020. Let me explain to you what that means. If I have a short sequence, I'll be able to have something, an image very sharp, but noisy because of the photon noise, the shot noise that is inherent to photons. If I take a very large number of frames and I do not compensate for movement, of course, I'm going to have a blurred long sequence. With motion compensation reconstruction introduced by Mohit, it was able to achieve both images that are sharp and at the same time with relatively low noise. So this is an example of a 0.03 photons per pixel per frame over 2,000 frames that was achieved. And here, obviously, the image doesn't tell you much until you reconstruct it. And this is done by essentially compensating for movements, at the same time performing superposition of the images. Another application of quantum burst photography is high dynamic range. So in this case, of course, you use the fact that, unlike in conventional cameras, where once you reach the full well capacity, essentially you cannot detect any further increase of incident photons, and therefore you have a non-invertible image. On the contrary, in single photon cameras, you have a soft saturation, and therefore ultimately the total number of binary frames is the limit of the saturation. But this way you can essentially able to reconstruct a much larger number of photons, a much larger range. So this was published in a paper by Ingle, Felten and Gupta recently in CVPR 2019. It turns out that you can actually represent it mathematically, and this allows you to reconstruct images with high dynamic range. This is an example of a long exposure with a lens flare and short exposure where you're able to reconstruct a shorter high emission, but essentially you're incapable of detecting low illuminated devices. And then here with the quanta burst photography, you can recover both bright and dark regions. So I'd like to conclude the talk with a few considerations. Well, first of all, with the help of CMOS compatibility of SPADs, it is possible to essentially achieve or take advantage of Moore's law. And so this was achieved with more and more larger and larger detectors, and also the use of more and more advanced technologies. But actually that's not the end of the story, because in the future with the introduction of even more advanced technologies, it will be possible to embed intelligence in the SPAD arrays. So I'm looking forward to the time where it's going to be possible to embed not only neural networks, but also much more complex, very complex algorithms. These are the devices that we detected, that we implemented over the years, and I'd like to attract your attention not only on the megapixel and the piccolo that I presented earlier, but also on smaller devices like this one that was able to be used in microscopy, or these devices that could be used in biomedical applications. And this essentially shows the large diversity of SPADs that can be implemented nowadays. And of course, industry has been very prolific in new products. So you've seen Novovid's imagers, but Pi imaging technology was able to capitalize on this type of detectors for using detectors for spectroscopy, for microscopy, and also for fast imaging. But also Canon has introduced a SPAD camera. ST has introduced a single photon measurement device that you probably have in your phone today. And of course telemeters and PET as well as gamma detectors. So with this I'd like to conclude, and you can get information from this website, and maybe some of you would be interested in the future to use our detectors, and we're very happy to collaborate with industry and academia. And this is our user group meeting, that is a biannual meeting in which everybody that is using our detectors is coming and giving presentations on their applications. And thank you very much again for the invitation, and this concludes my talk.
Thank you, Edoardo. So we have quite a bit of time for questions. Yes. Just wait for the mic.
Oh, I'm sorry. Oh, thank you. Yeah, that was very interesting. I'm not extremely knowledgeable about semiconductor devices, so my question might be naive, but is it possible in X-ray energy waveform, with X-ray energies, photon counting detectors can resolve energy, either in bins or so, and they use that, for example, to do spectral analysis. So could you do that with SPADs? Have energy resolving SPADs that would allow you to do like color imaging?
Yes, I'd like maybe to show you one of the slides that I did not show in the interest of time, and this is this one. This is an example where we are using one type of grating for X-rays, followed by an intrinsic grating obtained with the detectors, with SPAD detectors. In this case, we're going to need to build detectors with a pitch of 5 microns or less, even 2 microns essentially. The idea is to use it with for dark field X-rays. Dark field X-rays, you'll be able to detect features that are undetectable with conventional X-rays today, and this is really thanks to the use of detectors in combination with gratings and also with scintillators that are especially designed for this application.
Any other questions? Yes.
Hello. Thanks, Professor Charbon, for the great talk and comprehensive overview of what can be done with SPAD imaging. My question is more about on the consumer application side. So applications like mobile imaging, handheld cameras, the requirements there from the industry are sensors of resolutions with 50 or 100 megapixels. And my question to you is, how far away is this to be realized, and what are the challenges along that way that have to be resolved?
Yeah, thank you for the questions, and this is the reason why we built the 1.8 micrometer pitch indeed. So our plans are a 16 megapixels camera in the next 1 to 2 years. And after that, we are going to be using stitching for large format cameras capable of getting to 64 megapixels. Now, these are cameras that are still scientific cameras, so they're not consumer cameras. So for consumer cameras, I think with 1.8 micrometer pitch, we're not that far from the state-of-the-art of conventional detectors. That is at the moment 0.5 micrometers, if I'm not mistaken. So essentially, with 1.8 micrometers, we should be able to reach cameras that are relatively small and still able to achieve at least in the order of 10 to 20 megapixels. And I don't think this is too much far out. We need 2 pieces of a puzzle. One is a small pitch, and the other is 3D integration. And this is done, this is actually commonplace these days. So anybody can build a 3D camera, and I think the 2 things are going to be also relatively cheap in the future.
Any other question?
Hello. Great talk. I want to ask basically if you want to elaborate sort of at the end, you were talking about building or integrating neural networks and more advanced processing kind of directly on chip. What do you see sort of as the future of that?
Yes, this is another one. Let me just this is okay. This example is one camera that we built that is, you can see here, the camera, in this case, the camera utilizes Here you have a center detector array and surrounded by TDCs in this case. And essentially, neural networks can be built at this level here with the highly advanced technologies that can be placed, that can be used in 3D integration, typically 3 nanometers. You can build several million, or I would say several billion transistor cameras. And with these, essentially, you'll be able to build very, very extensive neural networks. So right now, we expect to have neural networks that can be reconfigured. And we already built a detector that is also the same size of this detector, 64 by 64 pixels, which is going to be reaching us in a couple of, it's actually in a month or so. And there we have a reconfiguration that was used for building 3 layers of 3 hidden layers and a total of 5 layers of neural networks in a almost fully connected graph involving almost all the pixels. And with this way, with 64 by 64, we are able already, now we simulated, we were able to achieve the total elimination of histograms in 3D vision, and also other things like non-line of sight reconstruction, and also the classifications of objects. And all that is done with a relatively small detector, but we think that this detector is highly scalable and we'll be able to extend it to several megapixels with the underlying neural network. So I think the future is bright for AI cameras, and I think also the AI cameras will be able to follow the expansion into the number of pixels as well.
Okay, with that, let's thank Professor Edoardo Charbon one more time. Okay, so now we have one invited talk before the session ends. I'd like to introduce Professor Mohit Gupta. Just one second.
Yeah, can I put it on top?
Oh, yes, we can close this. So Mohit is a associate professor at the University of Wisconsin-Madison. He has done extensive work in single photon imaging and has actually, well, he chaired ICCP 3 years ago in Madison, and has received the Best Paper Honorable Mention from ICCP 2014, as well as a ICCV MAR Prize Honorable Mention in 2019. So let's welcome Mohit.
Thank you. Thanks, Kiros. All right, hi everyone, morning. Already did a great job talking about SPADs and Quanta sensors from a hardware standpoint. So what I'll try to do is to continue the story from a slightly different, but hopefully a complementary perspective. I want to start by talking about how over the years, imaging technology has grown hand in hand with the downstream image processing and vision algorithms that make sense of the captured images. When we had films, we could do things like dodging and burning. These were really physical processes for enhancing the image contrast. So these were more global image level operations. But then we had digital cameras, and suddenly we got ready access to visual information at the granularity of pixels. This, as we know, was a game changer and played a humble but important role in the ongoing computer vision revolution. And again, one of the key factors here was access to information at a finer granularity, that of pixels. Now, we can think of a pixel as a bucket that collects light as a stream of photons. And usually for conventional cameras, we typically capture hundreds to thousands of photons before a camera can create a reasonable image. But as Edoardo mentioned, now we have SPADs, sensor technology, where we can access visual information at an even finer granularity, that of photons. And we know that we can't go any further. That's the limit. So a spark pixel here can be thought of as a teaspoon, not as a bucket. It can hold one photon at a time, but it detects that one photon quite reliably. Now, there are different modes of operations of SPADs, as again Edoardo alluded to. For example, SPADs can return precise timestamps for each photon, which is useful for applications like LiDAR, microscopy, etc. But I'm going to be talking about a simpler version where a SPAD returns a binary measurement. It returns a 1 if the pixel sees 1 or more photons in a given exposure time, and a 0 otherwise. So the measurements are binary. They're also random just because of the randomness of photon arrival. So we can think of these measurements as binary or Bernoulli random variables. And we can write the probability of the measurements being a 0 or a 1. So phi here is just the mean brightness or flux at the pixel. And as you can see, higher the flux, higher the probability of the measurement being a 1, as it should be. Right? So a single photon or a Quanta camera is just an array of these SPAD pixels taking these random binary measurements. And here's an example scene captured by a Quanta camera. So we get a series of these noisy binary frames, and each individual frame here is noisy and heavily quantized. Really, there's only one bit of information. And at first glance, it may be hard to figure out what's going on here. But we're going to use this as a running example, and I'll show a more interpretable version of this scene soon. But one thing I want to point out here is that there is a very limited amount of information in each of these frames individually, but we can capture these at very high speeds, reaching up to 100,000 frames a second, and maybe even faster, which is going to be useful. Here's another visualization of the photon cube. There's X, Y, and T, the time dimension. And what we've done is just really laid out these frames over time. And again, as we expect, brighter pixels record 1 more frequently, and the darker pixels are 0 more frequently. So this was a very quick primer on how, on Quanta cameras and their image formation model at an intuitive level. Next, I want to talk very briefly about what we can do once we have access to such photon level information. And Edoardo already mentioned a few things. And here's a nighttime image as an example taken by a handheld camera. There is low light, so you need a longer exposure, which creates blur and saturation. But if we start with a photon cube, we can design algorithms that track the motion of photons and aligns and compensate for it. So now we can start getting high quality photographs, even when there is not enough light and when things are moving around, which we all know is a hard problem. So there is the promise of ultra low light photography in photon-starved regimes, but somewhat counterintuitively, at least it was counterintuitive to me, these do quite well at the other end of the spectrum as well, when there is too much light. So here's a scene, and again, this is something Edoardo just showed, but with conventional CMOS cameras, there is a huge, in this scene, there's a huge dynamic range, about a 1 to a million. So we see both saturation and noise. But since we are, at least to first order capturing individual photons, we are able to mitigate saturation, this phenomenon of soft saturation that Edoardo mentioned. So we get high dynamic range as well, to the point that we can now resolve details in this bulk filament as well. So there are these very practical, very tangible imaging capabilities that we can get from SPADs. And again, Edoardo mentioned several more. There is LiDAR, there is microscopy. But maybe at a more fundamental level, the fact that we are starting from photons, the units or quantas of light, it really lets us explore the limits of computational imaging, at least along one dimension. So it lets us try and understand the bounds on the amount of visual information, and maybe how to design algorithms that can extract that information. So talking about designing algorithms, this is challenging for a couple of reasons. First, the raw data doesn't look like normal images or videos, and this is not directly amenable to conventional vision and image processing algorithms. But perhaps even more important is just the sheer amount of data. Even for a modest resolution of like a 1 megapixel Quanta camera, the raw data can be orders of magnitude, not just a few percentage points, but orders of magnitude beyond what traditional compute can handle. And at that point, it is not just a mere inconvenience, that can be a showstopper. So in my mind at least, this is as much of a computing problem as an imaging problem right now. So what we need to do is design a new class of photon-level operations or manipulations which preserve as much information as possible while somehow squeezing this data through this very narrow information bottleneck between the sensor and downstream processing. Another challenge here, of course, is that by necessity, almost these operations have to live close to or even on the sensor where we have very limited compute resources available. So they can be too heavy. So with all these constraints and requirements in mind, let's maybe start designing some simple manipulations on these photon cubes. Here's the photon cube. One of the simplest things we can do is really just add these frames over time. What we get is something close to what a conventional camera would capture. P here is the number of binary frames added, which is a measure of the total effective exposure time. So in a way, this is somewhat comforting that if nothing else, we can always create images that a conventional camera can capture, that a conventional camera would take. But since this number of binary frames, that parameter, that's a purely software construct, we can now produce images with different exposures. So here is a couple more, but just using different values of t after the fact. Which means now that we can compute these different exposures in a purely software-defined manner. And the nice thing here is that these virtually generated exposures are aligned, both spatially and temporally. So we can merge them easily if you wanted to create high dynamic range, etc. So we can take this a step further. Instead of simple sums, we can take weighted or coded sums. For example, we can use these random binary masks as spatiotemporal codes to create these coded exposure images. And if you zoom in, we can see this coded exposure, coded motion blur here, which encodes the underlying scene motion in this image. And then from here, we can design inverse recovery algorithms to reconstruct a video from this single coded image. And this is not a new method by itself. I mean, this is essentially a compressive video imaging, which has a long history, at least in this community. But now we are able to emulate these compressive video cameras using these random binary masks on photon cubes. One thing I wanted to point out quickly is that so far, one of the main ways to capture these coded measurements has been using spatial light modulators and relatively involved optical setups, like this one here, which we did a while back. But now, with these Quanta cameras, we can compute these optical projections computationally, which is more convenient. It is more convenient, but also gives us the flexibility now to create multiple such coded measurements simultaneously, again, which would have been hard. I know there's been work here at Toronto Kairos and who designed multi-bucket cameras. So essentially, this is same functionality, but again, done purely computationally. So this in turn lets us capture more challenging dynamics like this ball creating a splash of water, which otherwise may have been hard with just a single projection. So we have looked at these simple sum operations over time, which is like an integration over time, but we can now take it the other way. Instead of integration, we can compute derivatives or gradients, which is also a linear operator, so relatively simple. So as an example, temporal gradients tell us about changes at pixels, which is how event cameras work, by the way. So these are cameras where a pixel responds only when a significant change happens. And these cameras, these event cameras, have been quite popular in the robotics and vision community for quite some time. So what we're saying now is that starting from these high-speed photon detections, we can compute temporal gradients and maybe emulate event cameras. Here's an example. There's a fast-moving wheel and the corresponding events here. So here, blue means a pixel sees a big positive change, so positive gradient, and red is a big negative change, so negative gradient. The thing to note is that all other pixels stay quiet because they have nothing interesting to report, right? Here is just another visualization of the events laid out over time as the wheel rotates. And once again, as before, this is a this is a purely software-defined construct. This is now a software-defined event camera. We can now get both intensity and event frames simultaneously because these are really captured with the same camera, so they're naturally aligned and registered together. Now, of course, we can always get these two things by using two separate cameras or sensors, one normal and another event camera, and then we can fuse them. But then, this increases cost and complexity, both in hardware and for algorithms. So it would be nice if we can get both of these simultaneously from the same device. So far, we have looked at projections along the time axis, straight along time. So here, again, if we simply add these binary frames, we again get an image like this, where this falling die is blurred, but everything else is sharp. Again, as we expect, this is an image like a normal camera would capture. But now we can compute these projections along other directions in this 3D cube. Something like this. So for example, we can integrate along a direction that matches the motion of this falling die, and that would create this kind of an interesting effect where the die is frozen, but everything else is blurred. It's almost like the camera was falling with the die, but again, this is a purely software construct, so we get this image without ever moving the camera. Right? We can create a stack of these motion images where one, we can freeze the motion along a specific direction in each of these images. It's kind of like a motion, like a focal stack, where we vary the focus. But now this is for motion, and much like a focal sweep, here we can create a motion sweep, where we sweep across different motion amounts and motion directions. So in this scene, for example, different cars moving with different speeds come into focus at a different time. And then from here, again, similar to focal stacks, where we can create all in focus images, here we can create an all frozen image where all the objects appear sharp with minimal motion blur. Right. And finally, this is my personal favorite here. We can also integrate along non-linear trajectories, for example, a parabolic trajectory. This creates this interesting looking image where everything appears blurred now. But the cool thing is that everything is almost equally blurred. So sort of a motion invariant blur, which also, it turns out it also preserves high frequencies in the image. And what that means is that with a very simple deconvolution, we can recover a sharp image. By the way, if you have not seen this paper from almost 20 years ago now by Anand, Bill, and Fredo, I would highly recommend it. I read it as a grad student, and it still remains one of my all-time favorites. So, and this result was just a quick tip of the hat to that paper. So, just to summarize, we said that with very lightweight computational operations, we can turn a SPAD into many different imaging modalities, sort of like a Swiss Army camera, if you will, and possibly also get multiple modalities at the same time. From a user's standpoint, you can imagine kind of getting this drop-down menu of sorts where they can choose from one or maybe even a combination of different modalities based on their requirements. Right? Then they can make this decision almost on the fly based on the application requirements and based on the constraints. Going forward, an intriguing question here is that there are these different kinds of cameras that we've talked about that we can emulate. We talked about a conventional camera, high dynamic range camera, high speed camera, event camera, and even a moving camera. We have seen these examples, but are there others out there? Right? Can these Quanta cameras provide a sort of primordial soup for evolution of new kinds of imaging modalities that we haven't even thought about so far? So we were talking about these event cameras earlier, which are the poster child of resource-efficient vision. So again, these are cameras where a pixel sends information only if it sees a change, otherwise it keeps quiet. And these are designed to capture high-speed dynamics while keeping the bandwidth and data requirements as low as possible. Right? And this is the same scene, by the way, as viewed by a normal camera. The normal camera is just too slow to capture the high-speed motion. With high-speed camera, we do capture the dynamics of the slingshot now. But there are two problems here. One, the images are noisy. And two, we pay a heavy price in terms of the data volume here. So keep an eye on this green number here. This, for example, is something that will easily saturate the transfer protocols like USB 3. So event cameras, the goal was to try somehow get the best of both worlds, capture high-speed dynamics, while staying parsimonious in terms of the amount of data. But again, the trade-off here is that these events are extremely lossy. Remember, these essentially encode only temporal gradients, but they lose the absolute flux information. So what that means is that if you need intensities, which is a must for most, if not all, computer vision tasks, then we have a problem because we've really lost that information at capture time itself. We can try to recover these intensities from the event streams, and this is a result of a state-of-the-art event-to-video model. It sometimes works, it may not always work, because again, too much information has been lost at capture time itself. We just don't have enough spatial detail here. And if we start with videos like this, it does impact downstream vision tasks. So it's a quick video of a person playing tennis. This is as seen from, reconstructed from a conventional event camera. You can maybe get the overall structure here, detect the person, but you lose finite details like the racket and the ball. What we'd ideally like is something like this, where we are able to recover enough information to detect the person, the racket, the ball, even in this difficult high-speed motion scene, while also staying parsimonious. And it almost seems like no one imaging modality can do all of these. So this is where we start borrowing principles from multiple modalities. For instance, we designed a new space of generalized event representations, where each pixel still only transmits data when something interesting happens, so still produces a sparse spatio-temporal stream, but now each event, each of these dots here, instead of being just a temporal gradient, is a richer flux descriptor which preserves scene intensities. I'm going to skip the details, just very quickly flash through some results. I know I'm out of time. But broadly speaking, each event here has some richer attributes which encodes local spatio-temporal flux features. And the upshot is that now we are able to capture high-speed dynamics without paying a heavy data bandwidth and compute price. Again, as I said, keep an eye on this green number here. This is another example with fast, non-rigid deformations. There's a stress ball thrown at this mug. The normal camera we don't capture is not fast enough. A commercial high-speed camera does capture the deformations, but there is strong noise and quantization. With an event camera, again, you lose a bunch of details. You don't see the coffee mug at all. But with these generalized events, these are not as lossy a representation, so we're able to recover the world while keeping the costs low. Right? This is a tennis example. Again, I'm going to skip through this. But the key thing here is that once you start with better images and videos, it stands to reason that you will get better performance even for downstream vision tasks. Here you can detect the racket, the ball. And finally, it was just quite remarkable to me that now we are able to create these images and videos from Quanta cameras that work right out of the box with modern vision models. I'll finish by saying that we often talk about the importance of timing in research. Till just even a few years ago, all that we had was 1 pixel. So none of this would have been possible, but fortunately, we have witnessed a bit of a SPAD revolution in the last few years. So this may be a really good time to start thinking about building the right computational stack for these sensors. There has been a lot of excellent work, a lot from here, David and Kiros, Vivek Goyal at Boston, also Andreas at Wisconsin, a few other groups. So there's a lot of activity, but there's a lot more to be done. Thank you very much.
So, thank you very much, Mohit. Unfortunately, we don't have time to. So you're welcome to come meet Mohit and ask your questions. So this concludes the session. Again, let's thank the speakers.